Alright, I'm doing the test corrections. I kind of already started, but like this is take two. So I'm on the first page. Part C, train is moving, yada yada, drone. What happens if you hit the brakes? The drone will continue going forward because it will keep going in the direction that the train was, even though the train is stopping. Kind of like a person that's sitting down without a seatbelt in a car. Once the car suddenly stops, they're gonna keep flying forward till they hit something that stops them. Here on the other side, we have part B on this question, which is basically deriving an equation for the acceleration of mass. And we all know that acceleration equals F net over mass. I mean, who doesn't know that, am I right? And the force, the net force that are acting is weight perpendicular plus weight parallel plus the normal force minus friction, and weight perpendicular plus the normal force cancel each other out since they're basically going in the opposite directions. So we have F net equals weight parallel minus friction, and we know that weight parallel is mass times gravity sine theta, and friction is coefficient of friction times mass gravity cosine theta. So you get F net equals that, and then F net, that's F basically equals ma. So you get mass times acceleration equals all that. And then what do they have in common here? It's a g. So you factor the g out. So you get ma equals g m sine theta minus coefficient of friction m cosine theta. And you divide, in order to find for acceleration, you gotta divide mass on both sides. So you get acceleration equals gravity sine theta minus coefficient of friction cosine theta. You get part C, find the acceleration of everything, yada yada. Basically plug everything into the equation that we just made. So you get A equals 9.8 times sine 60 minus 0.3 cosine 60, which if we plug it into our handy dandy calculator, gives us acceleration equals 7.02 meters per second, since it's acceleration squared. Now on question 2, on this backside, we have this little pulley thingy going on over here. I already drew the free body diagrams for both systems without components. That's with the components. Derive an equation. Alright, so we start again with A equals F net over mass. And the forces that are acting on this one now is you have the big M, which is the heavier one, which is being pulled down by gravity. We have, of course, weight perpendicular, and then you're subtracting weight parallel because going in the opposite direction. Minus friction, and of course plus the normal force. These two cancel out. So what you get is the big M times gravity minus weight parallel minus friction, and they're being subtracted because this is the one that's pulling it down and that's what's slowing it down. And like we said before, weight parallel equals mg sine theta. Friction is the coefficient of friction, mg cosine theta. So what you do from here is, of course, F net, not F net, it's just acceleration now, equals mg, big M, g, minus small mg sine theta, minus the coefficient of friction, mg cosine theta, then divide that over the big M plus smaller m, because they're the two masses that are being acted upon. And from there, you factor the g out again because they all have that in common. So you get acceleration equals gravity m minus m sine theta minus coefficient of friction mg cosine theta, excuse my handwriting, over big M plus small m. And then find A, you gotta find acceleration again. You just plug all the numbers in. Big M equals gravity, which is 9.8, 101 kilograms, minus M, which is 51, sine 31, minus coefficient, which is 0.21, which is 0.21. Oh, whoops, there's not supposed to be a G there. It's coefficient M. So 0.21 times 51 kilograms cosine of 31 all over 151. We plug that into our handy dandy calculator. Should give us an acceleration of 4.23 meters per second squared. Now these questions. Question number 4 and question number 5. Acceleration due to gravity on Jupiter is right here, 24.842 meters per second squared. The radius is given to us at 69.9 million meters, which is 69.9 times 10 to the 6. What is its mass? So we're going to try and find mass. Forget all this. What we're going to need is acceleration equals the big G times mass over radius squared. In order to get this side by itself, we're going to multiply by r squared. So you get r squared A equals big G M. Divide that by the big G, and then you get mass. Mass equals r squared times A over big G. And I'm just gonna plug the numbers in from there. Big G equals 6.67 times 10 to the negative 11. So we get mass equals 69.9 times 10 to the 6 multiplied by 24.842 divided by 6.67 times 10 to the negative 11. And if you plug that to your handy dandy calculator, it should round out to 1.8 times 10 to the 27. First one, you got a planet of radius r and mass m has an acceleration of gravity of ag. The radius is quadrupled, but everything else held constant. What happens to the acceleration of gravity? So we have force of gravity equals g m1 m2 over r squared. And let's just say that this top part is constant. So we have of g equals constant over r squared. And let's say we multiply this r squared by 4, because that's what the question is asking. So we multiply by 4. Let's say we multiply by 2 at first. What will happen is that since we're multiplying it by 2, the effect on gravity is that it'll decrease by a fourth. And this can go on and on and on. If we do it by 3, when we multiply 3 times the radius, it'll decrease it by 1/8. So if we decrease it by 4, therefore it should equal the decreases